Okay, so in this part here, I will try to give you the motivation why the problem we're addressing here is actually relevant and why it's actually worth talking one term about mapping and SLAM, simultaneous localization and mapping. So why is this a relevant problem, and what are different things, different tools which are available in order to address, or you can say solve, but it's not really solved yet. So it's only solved in certain special cases, I would say. So how to actually address the SLAM problem. So what is robot mapping? So we need two words. A robot is typically a device. We are talking here often about mobile robotics. So we have a device on wheels or with legs. So something that can move through the environment. And this device typically carries sensors. And these sensors are used to observe what's going on in the environment. So it can be, for example, a camera. So it may take camera images. It needs to interpret the camera images. There are other sensors such as proximity sensors, which are sensors that measure the distance to the closest obstacle. So laser rangefinders are very common choice for that. There's actually one company who builds laser range scanners here very close to Freiburg in Baltic, a company called Sthe, which build pretty decent laser scanning devices that we also use on our robots in order to perceive the environment. These laser scanners give you in different angles the distances or the proximity to the closest obstacle, so you know that, for example, straight in front of me there's a 6 or 10 meter free space followed by an obstacle, and you get that, for example, with 1 degree or half degree resolution. You can actually use this information to estimate where obstacles in the environment, and you can estimate kind of maps which look like kind of floor plan maps. These maps are well suited to navigation tasks, for example. Mapping is a task of modeling the environment. So people often distinguish here between mapping and SLAM, which is simultaneous localization, and mapping and pure mapping. I'll come to this distinction in a second. What people mainly say is that if you do mapping, you know where the robot is. In simultaneous localization mapping, this is not the case. So it may sound kind of subtle to you, but it turns out that kind of the pure mapping problem is kind of known robot positions is actually pretty easy to solve, whereas the simultaneous localization mapping problem is not. So there are a few related terms which come up pretty often in the context of this course. The first thing is state estimation. State estimation means that you want to estimate the state of the system. So if you think about the position of the robot, then the quantities you want to estimate is typically kind of the XY position of the system in the environment and maybe its orientation. And you estimate the state of that system using, for example, sensor information like your camera images or the proximity readings from your laser range scanner. This is called so-called state estimation problem in general. You can estimate the state not only of robots, of let's say any system, especially the system which changes over time. You can estimate the temperature distribution in an environment, given you have a few thermal measurement devices. All these things are state estimation problems. And one typical instance or popular instance is so-called localization problem. That is what I've explained before. We want to estimate the pose of the robot. And typically we want to estimate it relative to a given model of the environment. So let's say if you have a robot, I provide a floor plan to the robot to say, take your observation and tell me where you are in that floor plan. So that's kind of localization. Typically you have a map given, you want to estimate where the robot is in the environment. Then we have the mapping problem, often referred to as, given I know where the robot is, I want to build a model of the environment. This can be seen, for example, if you have a GPS or very, very high precision GPS system. You know where the robot is at all points in time, but you don't have any idea what the environment looks like around the robot. So you may be able to take your, let's say, camera observations to build a model of the environment, to model the environment. So this is kind of the mapping problem. And the SLAM problem actually tries to do both things at the same time. I have no tools like GPS, I have no map of the environment, I just want to switch on the robot, it has no knowledge, and the robot, let's say, drives around through the environment and wants to estimate a model of the environment and localize itself with respect to this model. So this is kind of the problem we are going to address here in that course most of the time. Also, navigation and motion planning are two problems which are related to that. The reason for that is if you want to navigate through the environment, you typically need to know what the environment looks like. So you need to know where obstacles are, or if you want to plan a path and how to reach from this building here, one of the main lecture halls, you need to know that you have to drive through that door, turn right, turn left, open the next door, and then enter one of those lecture halls. And in order to plan those paths or those trajectories, you need to know what the environment looks like and where the robot is in that environment. So kind of SLAM systems are actually typically building blocks for doing navigation and motion planning tasks. Because if you don't have any knowledge about what the environment looks like or where you are in the environment, it doesn't really help a lot. So these SLAM problems have typically a strong impact on these navigational aspects. On the other hand, it's also the case that in order to kind of estimate a model of the environment and localize the robot, someone needs to steer the robot. Because the robot, if you just switch it on, it doesn't drive on its own. And depending on how you move through the environment, you will get better models or models that are worse. And so these are aspects we're actually probably not going to cover in that course, but just like to let you know that also the way you navigate may have an impact on what the environment looks like. Okay, so what is SLAM? Just said that before. We want to compute the pose of the robot and the map of the environment at the same time. And these are just for completeness, what I said before. So localization is estimate the robot's location, typically given a map. Mapping is typically building a map, often seen as giving the poses of the robot, and SLAM tries to do both things at the same time. Estimate a map of the environment and estimate where the robot is with respect to that map, a model that we build. And we do that kind of simultaneously. Sometimes you also find the term CML, concurrent mapping and localization, but this is kind of not that often used anymore. So kind of the term SLAM sounds nicer, and therefore most people actually use this term. So just as a small example, localization example. So this is a robot. So you typically often find this illustration of a robot, and this line here indicates the direction which the robot drives or looks to. And these stars should be landmarks, the things that the robot can observe in the environment. If you're here outside on our campus, all trees are pretty good landmarks. So I can actually use those landmarks, just the knowledge of those landmarks, to actually localize myself. Or just by observing the buildings we have in here. So given I know where the buildings are, I can actually localize myself relative to these buildings. So all these things are landmarks, and your robot needs to have the notation of what landmarks are in order to actually estimate its own pose. So the localization problem said we know where the landmarks are. So these are these yellow stars over here, 4 landmarks. Let's say these are trees outside in the green on the campus. When you have a robot that moves in the environment, you can actually measure where those landmarks are relative to it. So you know the angle and the proximity of those landmarks to its current pose. And if this is kind of the true trajectory the robot traveled, which is typically hard to estimate, but let's say, given we know that this was exactly the trajectory of the robot, but the robot thought that it traveled slightly different, because what the robot typically does, it kind of counts the revolution of its wheels to estimate how far it traveled. And you have a sensor which always gives you relative information. So what the proximity between me and the wall, if I'm standing 2 meters more to the left-hand side, these measurements will be 2 meters short. And so if the robot travels through the environment, and it thinks it traveled like this, although in reality it took this path, then it makes an observation, says, I think the landmark should be here given my observation, but I know it is here, so I should move more in the direction from this post to that post, so you see a small dashed line out here. So this is kind of a correction based on the observation. And the robot continues traveling, sees another landmark and landmark here. As it knows that these landmarks are here and not there and there, where it expects them to be from its measurement, it says, the only way to explain it is that my pose was wrong, so I need to move my pose towards this location. This is kind of the localization problem. So this is your estimate. This is where the robot was in reality. And typically, they don't match perfectly all the time. You want to minimize kind of the difference between what you estimate and where the robot is in reality, but you typically have no means to estimate or to know where the robot is in reality, unless you have kind of a special setup where you externally know where the robot was driving to evaluate your system. And so this is kind of your estimate, and this is kind of the ground truth trajectory. You can see here that for the ground truth trajectory, those observations here shown, these dashed lines fit quite well. Here, this is not the case. And then you try to say, where should the robot actually be so that this observation really observes this landmark, given that the landmark is here, then you will turn out that you have to move in this direction. The other example we may face is the mapping problem. As I said before, here, again, this is a real situation, exactly the same situation as before, and we know our position, so we actually know where we are driving because we have this super fancy great GPS, which tells us everything, but we have no idea where the landmarks are in the environment. So we do measurements, and observe them, we can actually then estimate where those landmarks are. Those guys don't fit perfectly, so these landmarks, the gray one is kind of the observed, what the robot thinks the landmark is, so gray is the estimate, and yellow is where the landmark is in reality. And the reason is that your sensor typically has errors, so no sensor is perfect. If you measure the distance to the tree, may say this tree outside there is now 30 meters away from me, but in reality it's 31 meters away. So there are always errors in the observation. And therefore, those landmarks are not perfectly at the location where you think they are. Typically, the more money you invest into your sensors, the better those estimates get, but they are typically not perfect. But the thing is, if you re-observe those landmarks over and over again by driving through the environment, you can typically actually reduce the error of your estimates and get more and more accurate. And so this is kind of the thing we can actually use here. If we do mapping, given the poses of the robot, we can actually estimate where those landmark locations are. The more often we observe them, the more accurate the estimates typically get. It kind of depends on how we have modeled things and what kind of distributions we use or which assumptions we use in there. But for example, if we assume that this error here is a Gaussian error, I perfectly know where I am, the error gets smaller and smaller and smaller over time. And the problem we have is actually the SLAM problem. This is what we're addressing here in the course. So the real trajectory of the robot, but we do not know those exact locations as in the mapping problem. And we do not know these locations of those features as in the localization problem. So we have to do both things at the same time. So the robot moves through the environment, estimates landmarks and says, so given what I measured while I moved through the environment, I think this is the first position of the first of the pose of the robot at the first time step, the second time step, and then those landmarks need to be here. You can see that this is something which doesn't really match reality, or there's a mismatch between the ground truth, which is this trajectory with those yellow landmarks, and those estimates the robot obtained. But that's something which is natural, so the models of the environment are typically not perfect. If I re-observe the environment over and over again, I typically, depending on which technique I use for estimating them, but in most techniques I can get more certain, more accurate in my estimate where I am relative to the environment and what the environment looks like. This is kind of the full SLAM problem, and this is what we're going to tackle here. Is there a question?
Yeah. When talking about SLAM, if we had like ideal sensors in an ideal environment, then would it be an easy problem? Like
so if you would perfectly know where the robot travels and you have perfect sensors, that would be simple.
Okay, and if you like make simulations, do you make like some kind of artificial error?
So what you can do if you do a simulator, you simulate the trajectory and then you add artificial noise to that system. So where the noise typically comes from in reality, let's say the wheeled robot, it depends on the diameter of the wheels. So if you have wheels which are inflated with air, depending on the air pressure, your wheels can get a little bit bigger or smaller, which makes an error. All the sizes of the axis and the grip of the wheels, everything is not perfect. So actually by just counting the revolution of the wheels, you typically end up in getting quite significant motion errors. And that's where one source of error comes from. The other source of error comes from your observations. If you think about a camera, let's say you observe the camera, even if you have the perfect tree detector, you observe the tree over there, given only a camera image, you only know where the tree is kind of given the angle of the system. You don't know how far it is away, because the tree would be exactly the same angle, but 10 meters further away. The camera image would look exactly the same, unless the tree would be a bit smaller. But so because it's just a projection on your image plane, and then you don't know where it is. If you go to a different place and then re-observe that tree by triangulation, you may be able to identify where it is, but this is always a process which introduces errors. And other sensors, how they work, they typically send out a light signal and measure the time it needs to until the beam of light or the laser beam hits an obstacle and is reflected. They just measure that time and can calculate the distance from that. But again, this is the measurement process, and the clock is not perfect, and you have errors in there. That's the reason why your observations are uncertain. Also a question?
This ground truth trajectory, what are these values and how we get these values?
Okay, ground truth. If there would be a perfect thing to get ground truth values, we wouldn't have any problem. Ground truth is the thing that God told me, this is a ground truth trajectory. That's it. The thing you can't obtain the ground truth trajectory in reality. What you often can do, that use some kind of external knowledge or external sensors that gives you a very good approximation of the ground truth. Let's say you have some external measurement devices with, for example, these motion capture systems, which use a lot of cameras and some artificial markers, which allows you, you know exactly the size of the markers, and given you observe them from multiple cameras, you can actually quite accurately track them down at a millimeter accuracy.
These are the values in your map. I mean, we have the map and we know that we say, okay, this is the ground truth and different position in the map.
So the ground truth is the thing you would like to have. So you want to come as close as possible to the ground truth, but you don't know the ground truth. If you would know the ground truth, you wouldn't have no problem, you just take the ground truth. But you typically don't have that. What I just wanted to say is sometimes you can build an experimental setup which allows you for this specific instance to determine the ground truth quite accurately. And then you can use this to evaluate how good your estimation algorithms are. But in the general case, we don't have kind of the perfect sender or the perfect thing which would give us ground truth. The ground truth is always something which we kind of externally use to evaluate a system. Or if you use a simulator that was raised before here. The simulator, you know exactly where your simulated robot was. And because you simulate the position of the robot, you simulate the observations, you can add artificial noise to that. But the ground truth in simulation is easy to obtain, but in reality it's hard or even impossible to obtain.
We have the map and these values are the relative position in the map.
So if you look to what you want to have, for example, is you have some coordinate system and you have the XY location of those features. So if you look outside here, you see there are 1, 2, 3, 4, 5, 6, 7, 8, 9 trees. And I give you the XY location of the trees given where I'm standing right now is 0, 0, 0, the ground truth reference frame. That would be your map. And then you start the robot up somewhere in that map and say, okay, where am I? So you might see a tree here, a tree there, a tree there. It must be here, that location.
So the 0, 0, 0 is the place you start and this distance from your position. I mean,
this is kind of an implementation detail. Typically in SLAM system, you start up the robot says, I'm at 0, 0, 0, and it just starts. Because it's its own coordinate frame, but there's nothing which needs to be there. You can also use 1, 1, 1, whatever you would like to have. So it's kind of just a convention of a reference frame. Any further questions so far? Okay. So why is this relevant? You see this robot over here? You may have seen that in driving through downtown this summer a few times. So this is one of the robots we developed in one of our European projects called Europa. It's a robot which is designed to navigate in urban environments, to perceive persons. And you can actually give the robot a task and say, go from here to Bertelsbrunn in downtown. The robot can actually find its way to go there. And of course it uses mapping technology in order to do these tasks. So it needs to build a map of the environment and localize itself in its own map in order to plan its trajectory towards its target location. And this showed that, given that you have no further information about the environment, that SLAM's a so-called chicken or egg problem. So you do not know what do you have before. Do you first have a map or do you first have a localization? The problem, we need to estimate both at the same time. And these two quantities depend on each other. So you typically need a good pose estimate in order to build a map. It's kind of the mapping problem. On the other hand, you need a map in order to localize yourself. So you need to build up the map and localize the robot at the same time or incrementally. And therefore, this is why it's often referred to as a chicken or egg problem, because the map estimate and the position estimate of the robot are strongly correlated. So if I know the map, localization is easy. If I know the pose estimate of the robot, mapping is easy. But doing both at the same time can be rather complicated. And so it's a pretty important task, because only if I have a map of the environment and I know where I am in the environment, I can actually use those models in order to create navigation actions. So to tell the road where to go to reach a certain target location where the system wants to go. So it's kind of one of the enabling technologies to develop kind of truly autonomous systems or truly autonomous robots, because if the robots cannot know the environment, they cannot know where they are, they can just be only kind of reactive things which react to sensor input and do something. And the tasks we do with a very reactive system are typically rather limited. So we actually need those systems in order to, for example, do good navigation tasks, or to know what the system should do, where should it go, which action should it choose.
Which kind of landmark did the robot use if it go from checking and tracking?
So in this system, we don't really use landmarks. We use kind of the raw scan data. So we use this kind of laser scanners. So these kind of these guys. So one is sitting in here. You can barely see it. Another one is over here. They give you proximity information in the environment, and we use kind of the raw endpoint data, so we know just the distance to the obstacle. So we don't use landmarks. There are different ways on how to address the problem. If you know what you're going to observe in your environment, landmarks are great. You have a good landmark detector, because it can dramatically simplify your problem. If you don't know what you're going to expect, it's really hard, because if your landmark detector doesn't work, well, there are no landmarks that you can observe, you don't have any observation. That's the problem. So depending on how much you know or how much you can engineer your environment, features can be great or they can be bad. So it's always a question what to choose. But we haven't selected features. A non-feature based system was used. So the second is that slime is kind of the central technology that you need in most robotic applications if you want to build up reliable, autonomously operating robots. And this can be examples in completely different fields. So you have things like vacuum cleaner at home or some other device which cleans your apartment. It should know what your environment looks like, and it should know where it is in the environment to determine on which path it should go in order to clean your floor. So if you look at these first vacuum cleaners which are available, like this Roomba robot, it mainly just was doing random walks. It was just randomly driving through the environment until it hit something, it turned around and continued driving. If the environment is not too big, at some point in time it will have covered the whole environment. Or as time goes to infinity, the probability of having covered the environment goes to 1. But that's really not what we want. So it's better if we can actually finish the cleaning task as quickly as possible, and for that I need to know what the environment looks like and where the robot in the environment. And actually the kind of second generation of vacuum cleaners actually use slime technology in order to do that. Other examples are aerial vehicles that need to, let's say, monitor factory environment or look for whatever hazardous things. So whenever systems need to autonomously cover an area just by observing it by its sensors, by doing some task, they typically need a map of the environment. With aerial vehicles, you can often deal with kind of GPS-like things that easy to drive outdoors, because air vehicles typically high up in the air, it's pretty good GPS receivers, but sometimes those robots, let's say, need to fly through a window in the inside of a building, and then they're completely screwed up if they only rely on GPS-like information. Underwater robotics, so there are big projects, especially in Australia, on reef monitoring and kind of estimating the quality of the animals or the coral reefs, especially Australia, invests a lot of money into that. Also here, localization is very important for those vehicles, because if they're localized, the likelihood of retrieving a vehicle is very, very low in the ocean. So you need to know where those systems are, and especially if they're underwater, GPS, all those things simply don't work. There have been underground tasks like exploring mines or even space applications, where you simply need to estimate where the robot is. And these are some examples. So this is the cleaning system developed by Evolution Robotics and not recently acquired by iRobot. This is one of the systematic cleaning devices. We have these underwater systems. So this is also a robot developed by the University of Sydney, Dr. White, one of the kind of pioneers in slime. And they use this device to actually monitor coral reefs and also need to know where that system is. They typically use sonar sensors, which give you also proximity information in order to estimate where they are. This is one of those examples of a robot driving on probably moon. So this is just an artificial illustration here, that's not a real picture. And this is one of the projects done at CMU on mapping abandoned mines around Pittsburgh, where they need to actually build models of abandoned mines, because sometimes mines collapse, and if you're planning this part of a city or you want to build your house, you would like to know if there's an abandoned mine in your house. So there are several applications that this is relevant. I have a few showcase videos here. So this one is actually the mint cleaning system. It's kind of the advertisement video. I just will show it for a few seconds. Very nice.
Set Mint down on the floor and press run. First, Mint covers the open floor area, digitally mapping the room as it cleans. Then, Mint spot things around furniture legs or other obstacles. And finally, Mint meticulously cleans edges and corners using its advanced perfect edge technology. It doesn't rest until your floors are spotless. And Mint isn't just for dry cleaning, it mops too.
Okay, so it goes on for a couple of minutes, but what you can see, especially from the beginning of the video, it was actually using a technology to estimate where it is in the environment. It was doing this kind of, if you look at the beginning of the video, they kind of a small box is kind of what they call North Star technology. You put it on the somewhere in the environment, and actually projects an infrared pattern to your ceiling, and the robot has a small infrared camera with a very little number of pixels, and tries to find this pattern in the environment, and then uses actually to localize itself. And this is why it can actually so accurately drive through the environment. And this uses, actually the system uses internally something which is related to the Kalman filter, uses an information filter to actually solve the SLAM problem. It really does SLAM. Next example is actually a system, the Europa system, which was recently in the news, which was developed here by the AIS lab in Freiburg.
Einen Roboter auf Wanderschaft in Freiburg zeigen wir Ihnen. Von Wissenschaftlern begleitet, musste die Maschine selbstständig ihren 4 Kilometer langen Weg in die Innenstadt finden. Das klappt mit Hilfe von Sensoren und Scannern, die 10-mal pro Sekunde die Umgebung analysieren. Nur an Ampeln mussten die Begleiter dem Roboter helfen, Farben erkennt er nämlich noch nicht. Nach 2 Stunden kam der Hightech-Wanderbursche unfallfrei ins Ziel. Solche wie Ihnen will die Roboterforschung zu nützlichen Helfern entwickeln.
Okay, this is also one of the examples where you see that systems that are not yet a product which is deployed compared to the vacuum cleaner, but this is one of the technologies which is very likely to be used for kind of future navigation systems, not, let's say, even outside cars. So you need to perceive the environment, you need to estimate where you are, and in order to get that high accuracy, you need some kind of mapping technology in order to achieve that. And there's another example of a bit more technical example. This was one of our robots driving here around the campus, and what you see here on top. So this is kind of the position of the robot, its trajectory so far, and what it sees. So these are kind of proximity information to the next obstacle, and here was kind of a limitation of the sensor range, so it cannot see further than that one. So this is an obstacle, this is an obstacle, these are obstacles. And you can actually integrate those information to build kind of floor plan map, which is what you see here, and you see evolving in a few seconds. While the robot is driving through the environment. So this is a current observation, this is how it builds its map, and you can actually, at least after it was driving around for a few times, you can actually guess that this is a computer science campus. So whenever it comes back to places where it has been so far, it can actually do corrections in this map. So you can see here the Mensa building, you see the surroundings. This is the building 79 where we are located. We are currently here in 101, which is over there. Building 51, 52 over here. This is a parking lot down here. And so these are maps, or typically kind of floor plan-like maps that robot can build if they use this kind of laser scanner-like technology and just estimate the proximity of obstacles and then integrate them into the map without using features. So coming back to your example, so you just integrate your raw observations and you can see this kind of not very sharp line you can see here, sorry for that. These were actually the bushes close to the, so over here, these are the bushes close to the train station, therefore they look kind of not that sharp as the edge of the house or walls of the house. Okay, so this is what systems typically technically look like, and by the end of that course, I hope that you will be able to implement systems which actually do exactly that. So given you have this sensor data, what the robot perceives, just those local observations here, and kind of the incremental movement estimates of the robot, to actually build up a full mapping system which tells me for every point in time what's going to be the best estimate of what the environment looks like and where is the robot relative to that map. So it's kind of the goal, one of the goals of this course. And then you can really build those systems from scratch, so really relying on basically no external, let's say, systems or tools, really build things up from scratch and understand the concept of those basic systems. Okay, so I think at that point in time, we'll just make a 5-minute break, and then we're going to continue with the course, with its introduction. Are there so far any questions? So whenever you have questions, you can also come to me in the next 5 minutes, and then ask me questions, anything you want to know. Okay, thanks. Please open the window. Okay, so then we can continue here and look a bit more in details into the SLAM problem. So what is a SLAM problem? I just roughly said so far we want to estimate the positions of the robot in the map of the environment. We put that a little bit into more mathematical terms. So what is given? So what do we have for, let's say, central commands of the robot? So this U typically describes the control of the robot. That can be how did the, for example, how did the robot move through the environment. And this is given by a sequence of commands which have been executed to the robot, like driving meter forward, or by so-called odometry measurements. Odometry means you have kind of a small encoder attached to your wheel. You simply count the revolution of the wheels in order to estimate where the robot was. The other alternative is you have these odometers which count the revolution of the wheels, which give you an estimate how far the robot traveled. So this is kind of these controls, these U1 to T different steps, points in time. The second thing you have are the observations, we call Z. And it's also a sequence of observations, and they strongly depend on your sensor. This can be camera images, this can be individual laser scans, this can be sonar proximity measurements, this can be GPS measurements, whatever sensor your system actually uses. This is kind of the sequence of observations that happen. And so this is what we have, what we can kind of record it just by recording the sensor measurements of the robot. The second thing we actually want to have is first the map of the environment, we call AMP. And again, this how AMP exactly looks like depends on your wishes, your constraints, on what you know about the system. This can be positions of landmarks in the example of the trees. This can be these raw measurement values that you've seen here while driving on the campus. This was a so-called occupancy grid map, which estimates for every point in the environment if there's an obstacle, yes or no. It's black means there is an obstacle. If it's white, it means there's no obstacle. And so this is different models on how a map can be represented. And we're going to estimate the path of the robot x0 to t. So typically different positions where the robot was in time. Let's say, typically in theory it's a continuous problem because of the continuous trajectory in which the robot drives. And we always, or in Yall systems, actually simplify that to, let's say, at discrete points in time, let's say every second or every 2 seconds, or whenever a new measurement arrives. Because if I'm driving without having a measurement, there's not that much I know, just know my uncertainty increases at the moment. And once I get a measurement, it makes sense to create a new discrete time step. So we assume that we have these discrete time steps, and this is also something, since all robots are kind of digital systems, that typically have encoders which tell us, yeah, one revolution of a wheel, second revolution of a wheel, third. I can take every of those events to create one of those discrete points in time. And if you look to techniques for estimating the state of a system in the environment or map of the environment, it turns out that, especially if you don't use the absolutely perfect, highly accurate sensors, that you need to deal with uncertainty because your sensors are not perfect, your motion is not perfect. So probabilistic approaches, that means approaches that use the concept of or use probability theory and explicitly represent uncertainty are techniques which are very well suited to solve these tasks. Therefore, basically, all successful systems use these probabilistic concepts. And if you want to very basically illustrate what the difference is, if you're in the non-probabilistic world where you say everything is certain, you say this robot is exactly here at this point in time, x equals whatever, 3.12 meters. In the terms of probabilistic things, you say, let's say, sloppy saying, the robot is somewhere over here, and this is my probability distribution. So it's very likely to be here at that point, so this location here may be the most likely host in this probabilistic system. Doesn't have to be, but could be. And then you use a probability distribution where you say, the robot is very likely to be here, it's very unlikely to be here. So this is kind of the difference between these two worlds. And these probabilistic approaches are kind of the key in order to address the simultaneous localization and mapping problem accurately. Not even for the SLAM problem, even localization on its own and mapping on its own is typically done using probabilistic techniques. So, in probabilistic techniques, it means we want to estimate this probability distribution. So you can actually read this. So this is a probability distribution. And what we want to estimate the path at every point in time. And the map of the environment. And then we have this strange bar over here, which you can typically read as given. And it's given the observation and the controls. So the stuff here on the left-hand side is what we want, and this is what we have. And we use these guys to estimate what we want. Okay. Any question about that? Okay. So next thing we typically need to identify is what are the dependencies between those variables. And we can kind of graphically illustrate this with typically a so-called graphical model. This is a typical graphical model. You see these circles over here. Every one of those circles represents a variable in my system. And we have those kind of light gray variables here. These are my controls for the motion estimate and the sensor observations. And this is what I have, these kind of shaded, light gray things. And what I want to have are here, so the white variables are the unknown variables, and the ones which have kind of this box around are those I want to estimate. And these errors have a special meaning. These errors in this kind of base network system, you can actually intuitively read as influences. Which means here, xt minus 1, the position of the robot at the point in time t minus 1, influences the position as xt. Which makes sense, because if I know where I was 1 second ago, I should have a pretty good estimate where I am right now. If I have no idea where I was at the last point in time, only where I've been 2 hours ago, I'm probably much less certain where I am. What this diagram also shows, for example, there's no connection between xt minus 1 and xt plus 1. What does that mean? So there's here no arrow from going from xt minus 1 to xt. What does that mean?
Your independence, I mean, it states you
There's no direct influence from xt minus 1 to xt. It doesn't necessarily mean that they're completely independent. It depends on what you know as well. So given that you know xt plus 1 is actually independent of the rest. Because if I know where I was at the last point in time, I can estimate where I am, and I don't care what was in the past. We call the Markov assumption. Okay. I can also read from this is, if I look, for example, to this variable xt, if I know xt minus 1 and I know ut, these are the two variables which influence xt, I can actually estimate xt. So because xt has a dependency on these two variables, given I have those two variables, I can actually compute this. And if I look to all these different variables which have incoming errors, I can actually only see here two different things. One is xt coming with an incoming error from its previous pose and from the command. That's part one. And the second one is from or the estimation of the observation I have, which is influenced by the map and by the cone robot pose, which also makes sense. So if I say what do I observe, it depends on where I am and what the environment looks like. And it doesn't depend on where I've been in the past, given I know where I am right now. This is the second thing. These are two models. This thing here is the so-called motion model. This thing here is the so-called observation model, to which we'll come at the end. What this graphical model tells me the dependencies between those different variables, the direct dependencies. And it also tells me what I'm going to estimate, because this is given by those boxes over here. So here I want to estimate m, the map, and the whole trajectory, given these shaded gray variables. Okay? So these are kind of my unknowns, these are my observed variables. Okay. What you see here is a so-called full slam problem. Full slam means I want to estimate the full trajectory or full path of the system and the map of the environment. There's a different variant of the slam problem, which is called the online slam problem. And here I'm not interested in the whole trajectory of the system, but only the last position of the robot. I don't care where the robot was in the past, I just care where it is right now, given the model of the environment. So whenever you have problems where the robot needs to make a decision based on where it is at the moment and what the environment looks like, you typically estimate the so-called online slam problem. And here you need to estimate much fewer variables. You don't need to estimate the full trajectory, just the last of those. So how does the graphical model for this kind of problem look like? If we go back one slide, what do we need to change to come up with the graphical model where only one estimate is? What do we need to change in this graphical model?
The shadow?
Yes. So the shadow changes, how do they change exactly?
Only the exterior looking at should
Yeah, so kind of this shaded area here only covers this variable. These variables are not interested. This is exactly how it looks like. This is the graphical model for the online slam system. What this means here, I want to estimate the position of the robot at the point in time xt plus 1 and the map, given all the sensor observations so far and the odometry observations so far. Okay? Okay. So these two problems are related. And I can actually express the online slam problem as a so-called by marginalizing out the post from the full slam problem. So given I know this probability distribution over here, estimate that one, I can actually integrate all previous pulses and then get this online estimate. And this is actually an action that most of the systems which try to do online slaying do. And every point in time they do a computation and solve one of those intervals. They start and kind of marginalize out the pulses and only estimate the current pulse of the system within that of the environment. Just to give you kind of the context for it. And then, as I said, express this exactly as marginalizing out all of the previous pulses. But when we are at that point in time and we go more details about the filter, you will understand that problem. Okay. So you may ask us, why is the slam problem actually a non-trivial problem? And the reason is the path and the map are both unknown and they are both coordinated, so they actually depend on each other. And this is one example, so this is what the environment looks like in reality, again. And let's say we have a sensor which observes landmarks, kind of a Gaussian noise, and we have also a Gaussian error in our motion. It's kind of our assumption here. Everything is a Gaussian distribution. This will, in the end, leads to the counter. So we have the robot which observes those landmarks and say, given I start here at this point in time, battery is going to die. In the beginning I started, so I 0, 0, 0. I observe the landmarks and these ellipses over here express the uncertainty I have in my sensor. So I know what the landmark is somewhere located over there. Okay? That's the first step. Then the robot actually continues and drives forward. While it drives forward, it executes motion commands, and this leads to an increased uncertainty where it is relative to its starting location. So if I say, relative to this location, I carry out a motion command, let's say go 1 meter forward. I'm here, but I do not know if I really drove 1 meter forward, perhaps 99 centimeters, perhaps 1 meter 10. And therefore I have an uncertainty around my current pose. This uncertainty is typically bigger than the uncertainty I had before, because motion introduces uncertainty. And this is shown in this example over here. So the robot moved forward, I have an uncertainty over here. Okay, next thing the system does is, again, it does observations, observes those landmarks. So the global uncertainty of this landmark is now bigger than these guys over here, because the robot had an initial uncertainty about its own pose. And it says, I don't know where I am exactly here, and I additionally have to add my measurement uncertainty, so this ellipse gets bigger. Okay. Continues driving. The uncertainty again gets bigger. And then the interesting part happens, that it actually observes a new landmark, and it also reobserves a previously seen landmark. And now it already has an estimate that this landmark should be, according to its previous observations, and where it is right now, and as a result of that it can actually reduce the uncertainty. Because I know it should be somewhere over there, I have a Gaussian distribution about the belief. I have certain uncertainty where I am right now when I observe this landmark, so these landmarks actually, or these positions, so it's two positions in the landmark, get correlated and their uncertainty increases because I have repeated measurements about the same thing. And this is here illustrated by these kind of small ellipses where they actually get smaller. this kind of reobserving things again leads to the fact that you have this strong correlation between, in the end, all landmarks of the Robotics process. Is this example kind of clear?
Does it mean recomputes its position in
Sorry?
does it mean the robot recomputes its position in every point where it was before?
This depends on if you do the full slam problem or if you do the online slam problem. With the full slam problem, you want to estimate the whole trajectory. In the online slam problem, you say, I don't care about the rest, I just want to know about my answer. So in the online slam problem, you would only care about this thing. Oh, you don't care about this one. But in the full slam problem, you will. Any other questions?
There are two ellipses on each landmark.
So this one. So this was the uncertainty before, and this is the uncertainty after reobserving it. So it gets smaller. And also the shape changes a little bit. Because you can see here, in this example, I had a bigger uncertainty in the direction, in the direction which is the proximity to the landmark, and I'm more certain about the angle where the landmark is relative to the robot's pulse. There you see these ellipses are kind of along the line towards the robot. So it's less accurate measuring the proximity to the landmark, and it's more accurate in terms of the angle. And therefore you kind of have these changes that the shape of this ellipse changes. Okay, clear so far?
Are all estimations treated equally? Or
So,
do
sorry?
they say, are all estimations treated equally? Or do they maybe value more recent estimations higher than the older ones?
So I already say all landmarks are equal. I don't care about the most recent landmarks, that they are kind of, they're more important, they may be more important to me, but this is not considered here in the estimation process. So
I know the landmarks, I mean just, for example, the ellipse on the second landmark, the smaller. So now I overlaid my new estimation with the old one, and then I found it's probably closer there.
So if you, this is not the case. So if you go around this environment, let's say 2 or 3 times, all those landmarks will be highly correlated in all their uncertainty limits. And really, depending on how often you've seen landmarks from different positions, so how much more observations we have them from different variables, the more correlated those variables are. That means the more I know about one variable, the more I know about the others. And as a result, also those typically the smaller the uncertainties get. But they are not treated unequally. So in the end, if you, for example, come to the common filter, which is one way for expressing this, these are the same. These are variables in your state space, but they're all treated equally. So don't say this landmark is more important for me or anything else. So they're all treated in exactly the same way. And the uncertainty is propagated according to the rules of probability theory. Any further questions? Okay. Second thing why SLAM is a non-trivial problem, and this is because of what I said before, data association. So data association is the fact that I do not know, given I have observations, if, for example, I observe features, to which features do these observations correspond in my environment model. So for example, if I have 3 landmarks located like this in my environment model, and this is according to the uncertainty I have about the robot's pose, and the robot observes 2 landmarks. It can be either case that the robot is over here and these observations correspond to these 2 landmarks, or I'm in this situation where the robot is here more on the right hand side and these observations correspond to these 2 landmarks. But this is a so-called data association problem. Unless I do not know, for example, that this landmark is red and that one is green, give me some indication how the data association look like. This data association is pretty difficult to do. And it's actually the case that making wrong data association typically leads to inconsistent estimates. So getting the real data association, the correct data association, is important in most SLAM systems. Okay, so there's then, after having discussed kind of what are the raw properties of the SLAM problem, I would like to look into what's called the taxonomy of the SLAM problem. So what are the different variants you find in here? The first distinction you find between algorithms is volumetric representations against feature-based representations. This was something which came up here before the question. So what you see here is the Victoria Park. It's a pretty famous data set or park in Sydney, Australia, University of Australia. And what they did, one of the kind of first big flight data sets, they took a car, mounted a laser scanner on the car, drove around to the park, and estimated the location of the trees. It was kind of at that time, large-scale data set. And you see those dots over here. These are estimates of those trees, so it estimates the trunks of the trees. You see sometimes that things are pretty not that perfect, and error measurements, maybe a person was standing there, no idea why. But what the system tries to do was to estimate the position of those tree trunks shown here by those yellow dots. And so the map representation is a collection of those yellow dots in their XY position. It's kind of the feature-based approach. The others may say, I just want to estimate, I don't want to extract features from my sensor data, let's say I have proximity data, and I want to estimate really the full 2D or 3D model depending on my sensor. So what you see here is a robot taking a 2D laser scanner and kind of tilting it, pen tilting it. It's actually building 52 and 51 here on campus. And you see kind of the full volumetric model of the building. Or this is done as a 2D laser scanner. This is just kind of like a floor plan map you obtain if you use the robot to drive through the environment. And here, this part of in this representation, you don't care all about features. You just say, I take my raw measurements, proximity measurements, and I integrate kind of those endpoints of those measurements into my model. And in this feature-based example, you say, I don't care about all these fancy observations I have. I kind of reduce them to features and use only those features. Both representations have their advantages and disadvantages. So feature maps can often be represented very compactly. I can typically nicely take one of those features out, let's say estimated Gaussian distribution. The more often I observe where the feature is, the smaller the uncertainty gets. Data association may be even much easier in those settings if I have a few distinct landmarks. And everything is super dense like here. It's really hard to say which of those endpoints covering the wall corresponds to those endpoints which cover the wall at the previous point in time, because the wall is, let's say, a flat, unique thing. So data association can be more tricky here. The environment representation can be bigger. It depends on some artificial discretization potentially. So there are pros and cons in kind of both representations. And both have been shown to work successfully. For the feature-based approach, you need to know what kind of features you're going to expect in the environment. If you send a robot to a completely unknown environment, the feature-based approach is sometimes a bit tricky because you don't know what you're going to expect. If you can perfectly engineer your environment, as you say, for example, you want to install the robot on a factory floor where you can change the factory to make it as easy for the robot as possible, and you glue some perfectly distinguishable landmarks in the factory floor, that may be easier for the robot. So it simply depends on what knowledge you have about the environment, what other constraints you have. Something else you often find are topologic representation against geometric representations. So in topologic representations, you can typically often find as these maps in subways, where you say, I have these different stations here, these are in Paris, but from this map, you don't have a geometric model that you say, this station is 45 degrees, or it's in this case, southwest of the second station. This is just, the only thing which this map tells you that those two stations are connected by a red trend line or something like that. So, compared to that, the metric representation, well, is typically, let's say, maps you know when you buy a map of Freiburg or of any other city. You get kind of these kind of map-like representations, and which every of those black boxes see as a building, and you know quite well the size of those buildings, so it's a direct metric representation or geometric representation of the environment. And so there again, advantages and disadvantages of both models. The topological model can be much easier implemented. And actually there are argumentations that we say humans also use a kind of topological representation in their brain in order to represent places, because typically, if I'm considering the, let's say, downtown Freiburg, I don't care if it is 4 kilometers or 4 kilometers and 2 meters away from me. I don't have this geometric knowledge here. But I see them more as places in the environment which are connected via some kind of paths. So there's some indication that people use a topological or metric topological combination. But in robotics, these metric representations turn out to be, let's say, at least more often used ones. Although they are bigger in storage, but they, for example, often allow the robot to better localize itself in those environments, or more accurately carry out certain tasks. So in most applications in robotics, you find actually geometric maps or partially combinations of both. That you say you take this kind of graph structure here and attach to every, let's say, load in this graph kind of a local geometric map. So you find combinations of both, but let's say topological maps are not that popular anymore today, although they have their advantages. Yes?
In the geometric, we don't have any correlation between different landmarks in the map, because if we need, we should calculate them somehow.
So the metric representation doesn't tell us, this is completely independent of if you have correlations or not. Kind of, this depends on your algorithm. You can even say that observations of the environment are strongly correlated also including the geometric case. Also, I mean, a feature-based representation is also a geometric representation because you kind of have metrics in there or geometry in there. Here, really, it doesn't have, it's just like a graph. They have nodes, and the edges just tell you, for example, I can go from A to B, but it doesn't tell you anything about the spatial arrangement.
How far is it done?
How far it is, in which direction. This information is often available in topological representations.
But in the geometry, we can.
In geometry, there's real the geometry of the scene. So if you look to the regular maps you buy, if you go here to downtown to one of those shops and buy a map, it's one of those metrical representations. These topological representations, you find the real world are really kind of this subway lines, because if you're in a subway, you don't care how far these individual stations are, how they're related to each other spatially. You just want to know which metro line should I take in order to reach my destination. Okay, further questions? Okay, so two parts of the taxonomy already covered. Next thing we often find is known versus unknown correspondence. This means in one part of the SLAM algorithms or in SLAM realizations, I assume that I can actually distinguish, for example, landmarks. This can be the case, although this also is not always so perfectly the case, if you, for example, have images and there are some features you can extract from images which give you I won't say unique, but a pretty unique signature, and you can actually use this in order to data associate to re-observe the same thing. This feature is exactly the feature I've seen in the other image. To kind of take into account the local surrounding of that pixel. But of course, if you observe something which is looks exactly the same, like exactly the same room in a different building, you again have that problem that they look exactly the same. But a lot of algorithms assume at least they have known data associations and others don't make that decision. So kind of knowing that this is your association versus I'm either there or either there. Some algorithms can deal with unknown correspondences, which is nicer, but typically more computationally more costly because they are more potential hypotheses about what the world looks like. So here you can say, either the world looks like this or the world looks like this. I simply don't know, but I may be able to maintain two estimates or two different estimates of what the environment looks like. Compared to the case where I say, if my known correspondences, it only can look like this. Second thing is this static versus dynamic environments. So there's one of those of the robot at the beginning of the demonstration and on the way to downtown. You can see here there are a lot of people walking around the robot, obstructing its scans. And so this is a very dynamic environment compared to this example here, which at least looks on this image pretty static because you don't see any people around. And static versus dynamic, although it looks like kind of small difference, in the end makes a pretty big difference in reality. Because you typically need to make assumptions in dynamic environments on how much the environment is allowed to change. Because you could consider in theory the example that your robot that drives around goes outside the building, re-enters the building. In the meanwhile, you've completely refurnished the whole building. So it looks completely different. There's really no chance for the robot to identify that. It's really hard for the robot to do that. The question is always, how much dynamic do you allow in the environment? And do you really want to model the dynamic and different aspects of that? Most SLAM algorithms actually assume a static environment. Let's say, world is static, that's my assumption. There's actually very little systems which actually explicitly take into account dynamics. Or the majority, at least, are static environments. Although this is a pretty strong assumption, consider the environment. If you look outside here, you actually see a lot of cars, you see cyclists, you see pedestrians walking around, which are all dynamic elements of the map. If you use the cars, for example, as your features, while they are moving pretty fast through the environment, you will get a pretty bad full system in your road. Questions about this dynamic static aspect?
Can you?
Yeah, go ahead.
closing the loop in the re-observation in the
Yeah.
stamp, and if there is something added, you just simply ignore it because.
Yeah, what else? What happens if everything which was there before has been removed and replaced by something else?
But do you know that you are in the same place you
How
were
do I
before?
know?
You close the loop. I mean,
Who tells me that? I mean, the robot has to identify this from its own sensor readings.
You start, for example, in somewhere, and the position, you know that position, and you come back to the same position. And so you can recognize you are in the same position, but maybe there are some new stuff, obstacles or landmarks are added or removed from.
So if I know that I'm exactly in the same place, of course I can model change, but typically the system doesn't know where it is.
When you close the loop.
Yeah, but who tells me that I closed the loop? The robot has to distinguish this from its observations. So consider you have a robot which starts here in summer, it goes to downtown Freiburg, waits until it's winter, and then comes back, and then I bring it back here. But I don't tell the robot that I brought it back here. It just says, this is not a computer science campus. It looks completely different to what I've seen in summer. Now everything is kind of white and covered with snow. Before it was kind of green and colorful. It's not the same place. So either you tell the robot, this is exactly the same place, it's fine. Then you can actually measure what has changed and what has not changed. But if the robot has to find it out on its own that there has been change in the environment, that's a pretty tricky problem.
Anyway, you build a map, I mean, you have the pose estimator, you have some localization.
Yeah, of course, but the problem is if your environment changes completely, you can't localize anymore. Like, I give you a map of Freiburg downtown, and then I kind of, I don't know, change the roads of Freiburg downtown because I changed how the roads were in Freiburg, and then I give you a map and you localize it. You walk and say, it doesn't match with reality, so you do not know where you are anymore. Just build a lot of tunnels through downtown and wormholes, whatever. You try to navigate and say, it doesn't look like what I know. So
it might be quite simple then. You do some look in this classroom and just change the position of this table then.
If you just have minor changes, typically systems can easily handle that. You just have, let's say, you are in this room, you change the position of one chair, the system will easily say, I'm still in the same place, and there's some mismatch, which can be either someone has changed it or just my noisy sensor. That's fine, but typically it becomes tricky. When you have in this situation, if a robot going here, with and without people, the scene looks completely different from the robot's perspective. Especially if you use the laser scales, it just measures distances to obstacles. Everything is covered with people, nothing of the scale looks like it was before. It's basically impossible to localize, unless you have some further assumptions or some model on how quickly things change.
And static would really mean that you assume nothing changes or almost nothing changes.
Exactly, assume simply nothing changes in the environment. Further questions? Okay. So next thing is small versus large uncertainty. This also can make a big issue. You say, what is the uncertainty my system has? So if this is the trajectory of the robot, it travels roughly like this, and you say, no, I'm seeing something I've probably seen before, and this looks like this place over here can be there. Or I can say I can be here, 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 or here. So be very huge uncertainty, very small uncertainty. And depending on how you represent your uncertainty, some of the systems cannot count as large uncertainties. They always have kind of only able to represent a limited uncertainty. If you think about a Gaussian distribution, that is often not that critical because you just kind of increase your sigma, your variance. Then you can represent a nice uncertainty. But there are other representations which, for example, don't use Gaussians, or even Gaussians can be problematic in certain settings with large uncertainties. Then you have systems which may not be able to handle these large uncertainties. So being able to deal with very large uncertainties is a nice property, but it simply comes at a certain cost. It can be computational cost, or how the uncertainty is represented, what the system can actually represent. The next distinction I would like to make is active versus passive SLAM. So active means that the robot actually steers itself or can generate own motion commands in order to acquire data, and passive means it's joystick. So if I take a robot and joystick it through the environment, that's kind of the traditional standard SLAM thing. So I've given observations, I've given commands, I want to estimate the map. So I joystick it, someone drove the robot. Or the question is the robot driving on its own? You can say the robot just drives on its own and looks exactly the same for me, but you can actually exploit that knowledge by saying, given that I steer the robot in a certain way, I may get better maps. or this may have, I may exploit the fact that I can actually drive to improve mapping. This kind of what's called active slam. There's something we are not going to cover here, of course. It opens a completely new field. So we just do passive slam here. We assume someone is steering the robot side and get the data, so we're not doing active slam. We're just discussing passive slam. Any question about active and passive slam?
But you usually have some kind of assumption then about who controls the robot?
I simply don't know anything. I just say the robot's driving, whoever drives it, can be human, can be a reactive controller, just always go straight or always go straight, some probability to turn, do some whatever random walk, whatever it does. And so at least it means in the estimation process of estimating the map, you don't explicitly consider the fact that you can control the robot. Let's say, I know this part of the environment very well, but I know nothing about this corner. So you may say, hey robot, go in that corner and look over there so I will get a complete map of the environment. That would be active slam. But it's really not what very few people do about active slam. Because it either you solve it trivially, or you solve it in a sound way and then it is super complex. That's all. So we doing here is kind of this passive slam. The other thing you often find are anytime, any space systems. Anytime, any space means anytime. I have to come up with a solution very quickly, and the more computational resources I have, the better my estimate gets. Or any space is, the more space I have, the better, let's say, my system gets. Or I have constraints, like I have a robot and a small embedded device which has only 64 kilobyte of memory. For example, like this mid-vacuum cleaner or something, I think brought 64 kilobyte of storage for the operating system and the SLAM algorithm. So it can store very, very little information. How can we actually perform as good as possible with having those resource constraints? Also something which gets more and more important, where you have the fact that the system needs to react within 20 milliseconds to some new event all the time, and for that it needs always the best coordinate estimate. So it has certain time guarantees and stuff. Finally, we have a thing of kind of single robot SLAM versus multi-robot SLAM. At one point in time, I have just a single robot which drives the environment, and once I have multiple, kind of a fleet of robots which is doing something. And depending on the representation you're using, multi-robot SLAM can be significantly more complicated compared to single robot SLAM, especially if you have the problem that you have two robots which, let's say, either communicate, but they do not know where they started relative to each other. So you can have two independent map estimates, and it's kind of an ill-posed problem to identify if, let's say, robot A sees a room, robot B sees a room, they look exactly the same. Is this the same room, yes or no? It can be that these two robots are simply in two different buildings which look identical. Everything looks identically the same, but they have no way to figure out if it's the same part of the environment, yes or no, unless they meet. You can detect that. So, therefore, depending on, in this multi-robot case, what assumptions you make, they are in the same building, or they start in the same place, or there's special initial uncertainty. If you make those assumptions, make it much easier, but in the most general case, where you don't have any further background information, it can be quite tricky. Okay, so as you've seen, this taxonomy resulted in a kind of huge branching factor, I think, with 8 different things, and everything can be solved either A or B, and you can add them all together. You end up with a large variety of different kind of variants of the SLAM problem. And as a result of that, a large number of SLAM algorithms has been proposed in the past. And it's one of the really big fields. If you go to huge robotic conferences, you see multiple tracks just focusing on SLAM, different sessions on SLAM and how to solve different variants of the SLAM problem. Because it's simply something that robot needs if you really deploy them in the environment, and you don't want to, let's say, manually build a map first, let the robot always in this environment, never change the environment. At some point in time, you need to deal with the process of building a map of the environment and localizing yourself in that. You actually say that the majority of concepts, at least the successful ones, use probabilistic ideas from probability theory. That means explicitly representing uncertainty and not assuming everything is exactly as the system tells. Like the system is exactly here, the landmark is exactly here. You always need to take into account the uncertainty you have in order to build up robust systems. And so the history of SLAM dates back kind of in the mid-80s, and I just have a small slide kind of just It's not super relevant, but just to give you an idea how things started. So 85, 86 were kind of two groups around Smith and around Bureau and White, which started to describe the geometric uncertainty of landmarks of features relative to each other. The first thing you said, let's take something probabilistic to actually describe the geometry of a scene. And then was at ICRA 1986, there was a discussion about a lot of people saying, how can we actually solve this kind of problem? And then there was kind of the first papers by Smith and Cheeseman, which was one of the first people who proposed one approach on how to do the slam problem. In the 90s, beginning of the 90s, the common filter-based approaches became popular. Also, people starting to provide certain proofs. I think a little bit later, the first convergence proofs of those systems, and use common filter approaches to build maps of the environment to estimate where landmarks are, where the system is. And then actually in 1995, so not later, the acronym SLAM came up. It was one of those international symposiums on robotics research in 95. And then from kind of 2000 on, there was a wide interest in SLAM techniques. Even a little bit before 2000, there were even alternatives proposed on how one could actually do that. And so we will also start in that course with the extended common filter, and then look into different approaches that have been proposed. Roughly, we can actually distinguish things into, let's say, three main paradigms that we find today. Let's say different approaches to address this problem. The first one is a common filter and all its friends, so common filter, extended common filter, unscented common filter, information filters, sparse extended information filters, all this kind of family of approaches which we also will discuss in the course. It's kind of the things that have been started with. Then as an alternative, particle filters have been proposed. A particle filter kind of doesn't assume this Gaussian distribution anymore, what the common filter does, and has a different way, kind of a sample-based representation, a non-parametric approach to actually estimate where the robot can be and its uncertainty. This is computationally to be more costly, but gives us more flexibility, but also has its limitations. And finally, we will discuss graph-based SLAM approaches, which have first been proposed around 97, I think, and then started to become popular in 2001, 2003, something like this, and are now the, let's say, most commonly used system, unless you have some special applications on these graph-based approaches. If you go back to our graphical model we had about the online SLAM system, I said already before we have kind of two different quantities, things we will, let's say, or models we will actually see very often in that course. The one is how to estimate the position of the variable xt given xt minus 1 ut. This is a so-called motion model, which tells me, given I am at xt minus 1, I carry out the motion command ut, where will I end up? It's kind of a local probability distribution where I am. This is the so-called motion model. The second one we need in order to solve this problem is the so-called observation model. And this tells me what is the likelihood of observing something given I know where I am and given what the environment looks like. So, given I'm in that room, given I'm here, I should measure, let's say, 4-meter distance in this direction. We have a probability model for that. So the motion model is something you can is something which describes the relative motion of the vehicle. So it's a distribution about the new pose or next pose of the robot given the old pose active for short. You can use, for example, different next slide. Different things. You can use it as a Gaussian. And let's say your Gaussian quickly gets the uncertainty increases while you move because you get more uncertain. So let's say the simple Gaussian model. You can have actually non-Gaussian models. This is what is often called the so-called banana-shaped distribution. The thing that looks like a banana. This comes from the rotational uncertainty you have in your systems. Or you can represent it by samples. Okay, this means kind of the more samples you have concentrated in an area, the higher the likelihood that you're actually there. There are different ways of handling that. What I typically need to do that is, given two positions in a certain coordinate frame, how can I actually describe the transformation to go from A to B? And this is something which comes from the Robotics 1 course, so can go more into details in that next week if this is needed. Depending on, we will discuss this probably after the course, how many have seen the motion model and an observation model, and depending on that, I will kind of next week dive a bit more in more detail or not. So you typically have your two positions of the robot. The first position of the robot is this x, y, beta with the bar, and it's always looking in this direction. And in the next point in time, it's standing over here. How can I describe that motion? I can do that by carrying on one rotation, which rotates here, translating the robot here, carry the second rotation. So rotation 1, the translation, the second rotation. And given I have those coordinates, I can actually compute the odometry information using this equation here. So the translation is just the distance between the centers of the robot, and then you have kind of the rotation 1 and the rotation 2. It's an 8 times function. The other one just subtracting the angles over here. And what you can typically do, you can add some noise to those terms, the rotation, the translation, another rotation, and then you actually get this kind of banana-shaped distribution. Because if you have an error in your rotation, you cannot get this banana shape. And so if you need more information about this, Introduction to Mobile Robotics, chapter number 6, or slides number 6 covers that, or the Progressive Robotics book, chapter number 5, you find all the details about these motion models. But as I said, if people do not know anything about motion models, I'm happy to give a short kind of 50 minutes wrap up of that next week. So who knows about motion models and says that's boring, and who wants to know? So who wants to know more? 1, 2, 3. So approximately half the course. So we'll at least cover that with kind of 15 minutes, giving the key ideas of this motion model next week. The same holds probably for the observation model. The observation model is again distribution of an observation. So how likely is it, for example, to observe an observation given that I'm at a certain pose? And for example, I know what the environment looks like. And this kind of relates the sensor measurements and the robot's pose to be given an answer after you don't write the map versus here. And the map is the same for all of them. Again, you can have different models like the Gaussian model where you say, given the landmark is in this direction, and then have a Gaussian distribution of where you see it. Or you have a non-Gaussian model. This is one of those typical models you can actually learn from data. We say it's quite likely to get a response before the thing I would like to see. And then you have something like a Gaussianish, but not perfectly Gaussian. It's another strange thing over there. And for those of you who haven't seen the motion model, they probably haven't seen an observation model, so I'll also try to cover that. And again, if you need more information about that, Introduction to Mobile Robotics course, chapter 7, or the Progressive Robotics book, chapter 6, provide you a pretty good idea of what's going on. We don't need that in all details in this course, but at least you need to understand the concept of a motion model and how this works. So, if you have never seen that, I suggest you try to read that chapter, at least look a little bit into that, and I will also give you kind of a short introduction, it'll take 15 minutes for each model. Okay, so to sum up, mapping is a task of building a map of the environment. Localization is a task of estimating the robot's pose in this environment. SLAM means doing both things at the same time. We distinguished full SLAM versus online SLAM. And in full SLAM, we are interested in estimating the whole trajectory of the robot given the data. And in online SLAM, only the last pose. And we also presented kind of a rich taxonomy of different SLAM variants you find out there and different ways to solve that. For literature overview, you have one of these handbook on robotics, Springer handbooks. And the first edition is chapter 37. And you also have here the part introduction of the Springer book, which also discusses this taxonomy in more detail. And on motion and observation models, as I said before, Progressive Robotics book or the course. And as I said, I will kind of repeat the key basics of these two models next week as well. Any further questions at that point? Again, if you have any questions, let me know via email, via the question and answer system online, or come to my office, visit me. And whenever you have feedback, just send me an email. I'm happy to take that into account. Okay, thank you very much.